Acho que faz uma outra atividade. Por exemplo, né? Sei, tu não sentido.
Right? So the is 1 centimeter plywood, 1 centimeter foam, right? So in case you can't see, write it quick. Everything is 1 centimeter. Plywood, plastic, and the plywood. Which way heat will flow here? Right? 32, right?
One here, right?
Huh?
You see everything one here, right?
Yeah, everything is 1 cm.
Alright, but this is the actual question.
Yeah, well, I'm going now. That's sketchy graph. Right, sketchy graph. Thickness of plywood. Same effectiveness as foam. So you're taking out foam. Okay? Real similar to the last thing. Right? And then we take a look at radiation. What did K values last thing? Wasn't this, right? Oh. Finally looking at a similar. Yes, ma'am. No, ma'am. Sketchy graph. Next thing. Until you come on the board and do this first. Until you clear out the side here, right? Down in the back. Quiet down in the back there. Well done. Excuse me, oh, yeah, okay. Finish your first now.
Yes. Where please?
Question there. Hi, yeah, come on.
Yes, stop it. Are you finished question then?
Los demás ya. Right, after you convert, finding power, right? Right, but which one you replace it again, the foam, right? Place the foam.
So we took minus.
No, yeah, sorry.
They took minus here because it's dance, yeah.
Oh, yeah, Jason.
Yeah.
Right, take up somebody can graph that one.
Sorry,
I think to be one way of the graph.
give me some of that. Still. So that's any that new idea.
The chunk is.
Please make it. The new,
You want to see what?
I tell you, ready.
With which one?
The number 3.
Right, you're done in part one, right? So part one, you have a graph. The graph has no negative parts. It starts at 30 degrees. Right, just of course you use a ruler and just cut it up evenly, right? So the temperature here will gradient like this. Here is much sharper, and here is the same place. And the value it will stop at 2 degrees. All right. Can you see?
Nah, really not.
That's it. Please make sure that these two gradients are the same, right? Remember that foam is the poor conductor, so therefore the gradient here is larger, right? Next, they want you to write thermal conductivity of plywood is 0.24, plastic is 0.12, thickness of plywood to replace the foam. So you want to replace 1 centimeter of foam. I will get in centimeters first, right? And then I'll convert it. Now let's take the meter. Okay? Right, 0.01, thermal conductivity 0.12. I would like to replace that with plywood. No, I should not. Right, technically, you kind of, you have to work, look at the unit for thermal conductivity. Watts per meter per Kelvin. Right, so you should like ideally work in meter. Right, cross multiply, solve for X. What you all got? Cross multiply and solve for X. Cross multiply, solve for X.
0.2.
Cross multiply, solve for X. Right, so we'll end up with 0.2 meters. Right, does it make sense? More about the conductor. Right, nice. And last part, they want to get the, oh, you gotta be careful here. They said using the equivalent thickness or otherwise, find the rate of conduction of the heat through a rectangular wall of 0.6 by 0.4 and deduce the temperature change on the interface, right? So they want temperature here and temperature here. Okay? I said that's a little bit different to what we've been doing all the time, right? But first, let's answer part one. The one the rate of heat flow, which is K E delta theta delta X. K is 0.24 because we're using plywood alone. A is the area, which is 0.6. A is the area. What do I write that? Right, K was what again? 0.24. The area was 0.6 by 0.4. Temperature change is 28, right? Right, that's 32. But what's the thickness, Darian? What's the thickness? Darian, I'm taking it for today.
Right.
What's it?
Zero point.
I have a calculator.
I don't.
You have a calculator?
I think bad.
We'll take it out because I'm taking it out. Right, yeah. What is the length? What is the thickness, Darian? What are you on your phone? Calculating what then? Thickness? What would the thickness be? What we got for foam? Huh? Right? 0.2 of the foam and then you have 1 centimeter, 1 centimeter. So here's 0.01, here's 0.01, and here's 0.1. So the answer was 0.22, right? How much is that? 7.31. Nice. How are we gonna use that now, finish to find the temperature on the surface here? Hold on. Very good, Vin. Which formula, Vin? Yeah, so he's actually correct. He's using this formula here. Right, we're using this formula. What's the value we using for P? 7.3 because 7.3 is what's flowing through everything. Right? What are we using from K? 0.24 because it's plywood alone. What are we using for temperature change? We don't know, we're trying to find out. Right? And then thickness is what? It's for the first piece of plywood alone. 0.01. Right? Because we're trying to find this temperature here. Okay? So we're only using the rate of heat flow through here. Right? So we're going back again. Part 3. Power is equal to K E delta theta delta X. Right? We're using 7.3, K is 0.24. A would have been the same thing, 0.6. What 0.6 and 0.4? 0.0. And temperature change, we don't know. And your steady thickness is 0.01. The other thing, find for temperature change. But you all got to the temperature change. Make it temperature is subject to the formula, right? So they want the temperature change. And then use that to find the temperature on the foam there. Is that how you follow what you're doing? Right? So they want the temperature on the foam side there. The interface of the plywood and the foam.
1.0.
That's not good. 0.01, eh? Check it out. Yeah, I got 12.7. The temperature change is 12.7. Here. So, what was the final temperature here via Matisse? If the temperature change is 12.7. Let's call that temperature theta1.
Right? It'd be 12.7.
30 minus 12.7.
I positive.
Right? What is that? 17.3?
Yeah.
17.3. Anybody got that online?
So
17.53. That's only the first part of online. Next part, you have to find theta 2. What temperature would that be, Pete? What would the temperature there be? What would the temperature to be? Pete. Yeah, no, Pete. No, don't, you gotta do back all that. Okay, let's start. Pete, what would the temperature change be on that second part there? Huh? Yeah. Pete, what would the temperature change be on this side here? Temperature change. What would temperature change be on that side? Temperature change. What was the first temperature change here? God. That was the final temperature. So look at there, right above it. 12.7. So what's the temperature change here as well? Same 12.7, right? It'll be the same temperature change because it's the same, everything is the same. Same rate of heat flow, same area, same thermal conductivity, same thickness. Okay? So therefore, Daria, theta 2 is what? 12.7 plus, so the answer is 14.7. All right, so the question wanted that. Online, you're okay with that? Kalina? Oh wait, Kalina, you were there also? Kalina, Katrina, was there otherwise? Was shots. All right, so that's what we did last day, right? So last day we did that thermal conductivity, right? Katrina, I had you also always there? In the waiting room? No, she maybe log in and can log back, log out and log. I don't think so. I would have seen it. Oh, she get disconnected, right? Okay, so all right, nice. So everything we did there so far, conduction. Let's move on to convection and radiation, right? Who can explain convection? From pump 5. Who can explain convection? Right, Pete? Yeah, go ahead. I'll not pick on Pete, but you are something on there, right? No, something again, right? You started off right. Go ahead. Think of a liquid being heated.
是
Yeah.
是definitely the heat at the bottom, right? When it go, the heat rises, it cools up, then it drop, then it up, then it rise, then it cool up, then drop. Yeah.
That's a good explanation. What? Okay, so when you heat the liquid at bottom, the liquid gets hot. For example, the liquid,
It rises.
why it rises? So when you heat something, it generally what?
Rises.
It expands. And if you expand, what will happen to the density? What's the fundamental density again? Density is what?
Then it becomes mass.
Density is mass over volume. So if the volume is smaller, density will drop. So the hot liquid is less dense. So the hot liquid will rise, and then the cold liquid will take its place.
That's why I say,
Right? And then you have the convectional current.
in the here. But then you can take a hit at that.
Yeah, it's my job,
Your challenge.
right? So for convectional currents, right? So I want you to remember this, right? If you have a liquid, it works with gases as well, right? If you're heating a liquid, right? If you're heating a liquid, if you apply heat to the liquid, right? Of course, the liquid here will get hot, right? And we know that density is mass on volume. So the liquid here, when heated, it will expand. When it expands, the volume is larger. Therefore, the volume goes up. And if your volume increase, because these two inversely related, your density will drop. Right? So what will happen is that the less dense substance will move up. Right? The less dense will now come here. And the cold, more dense will take its place. So you have something called convectional currents. Okay? And in convectional currents, it can work for liquids, it can work for gases as well. They behave the same way. Right here, as the AC gives up cool air will drop and the warm air will take its place. Right? So the same thing will happen here. So what you will notice about liquids is, convection, just like conduction, it needs a medium. It needs particles. That's okay? But the next one, moving on to is radiation. And for now, we don't have to learn about Bernoulli's equations and things, right? That's getting in UV. Right? What we're going to focus on is Pepper's law. Right? That has to do with radiation. Right? So if I have a body and the body at a particular temperature, the larger the body is, if the body is a black body, right, and at the right temperature, what it will do is it will radiate heat in the form of electromagnetic radiation, right? Radiation does not need a medium, right? With the medium there, well, good, it will still be radiated, but it doesn't need a medium, right? And the simple example is when the sun gives off its UV rays, the UV rays can still reach you. Okay? And there's a vacuum there, right? And the way it reaches it is via radiation. So Stefan now, he came up with a relationship that allows us to find the rate of heat flow from any black body radiation. And the rate of heat flow is given by temperature to the power of 4. So a real small temperature change will give you a large power, right? Or energy flow. By the area, that's why the larger the body, the bigger the radiation. And by the constant. Certain constant. Okay? If there's an interchange of temperatures from a hot to cool, then we'll see this version of the formula. T1 to the fourth minus T2 to the fourth. That's okay? All right. Let's go to the handout. Oh. Right, let's go to the handout. I have one more thing to do in this next to the platform. I don't interrupt. Right, convection here, we just talked about convection and so on, right? Most fluids expand upon heating except for water between 0 and 4, right? Water doesn't really expand within that temperature range. Contrast. Right, thermal radiation. Thermal radiation can be defined slowly in terms of the body's temperature as being the electromagnetic radiation it emits. At temperatures below 1000 degrees Celsius, the energy is associated almost entirely with infrared radiation. At higher temperatures, visible and ultraviolet radiation, right? Like from something like from the sun. When thermal radiation is incident on its body, some of the radiation may be reflected, some transmitted, and some may be absorbed and produce a heating effect. Second's law is mind very important.
What?
There's something more important than before. Okay, wait a minute.
I'm following big document. Live. Watch.
Pepper's law is used to determine the amount of energy emitted by a black body. Right? A black body is a body which absorbs all the radiation when incident on it. Okay? Huh? Okay.
Higasi.
Page 6. Right? It states that the total energy radiated per unit time per unit surface area of a black body is proportional to the fourth power. That's the area here, sorry. Right? This should be P is equal to Stefan's constant A by T to the fourth. All right? Just do me a favor, if you didn't write it down already, write down the formula and just write down what is Stefan's constant.
Radiation, it's it.
This one is
Radiation.
thanks to Jordan.
Yes.
right? Write down the other version as well, T1 minus T2, right? Remember, it's T1 to the fourth minus T2 to the fourth, right?
That's that one.
That's that one there, yes.
What's that one called?
That's when heat is being transferred from one temperature to the next via radiation. Online, you're hearing, right? Green side of pole here. Green is for every pure mass and phase class. You know, one.
So they are in class learning and
One temperature to the next via radiation. So like if the room have two different temperatures and it all radiating heat at different temperatures, you turn that. Huh? We have two versions of the formula. One with a T and one with a T1 and a T2. Right? One with the T1 and the T2 is when you have heat being radiated from one temperature to something else. So now that's good. Right? Ready? That's it. So we have to try one, right? Now it's here, right? Same formula down there, right? T1. All right, let's take a look at question, right? Right, take a little read, take a picture, you're not seeing it, right? Remember, all you have to figure out is when to use conduction and when to use the radiation formula, right? If you read it, it's not that difficult in part 1 and 2. Oh yeah. Try that, please.
City ends. You should be getting more time. The people, the right.
Right, because right, I might on Friday, so.
No, that's the key hundred one. So do you see one?
Sure, enough of anyway, yeah, same one. Ready? Marquis. Right? Yeah. Alright, let's go now. Let's start working this out, right? This will be done, yes, we can do the right ones. Okay, you write your line. Alright, let's see what we got here now. How are you helping them? Let's take a look at the company and how it's.
I get up to this bar, it's pretty second bar.
I don't know.
Well, I can see what you got.
Right, normally part three, and for part one and two.
Okay, but the second regular, I don't know regular.
Let's see. A block would serve with a surface area of 4.6. Cast iron. They give it thickness here. The interior wall of the stove is 650, that's the interior, and the exterior wall. The temperature of the surrounding air 30. Calculate the rate of heat of conduction, right? So P is equal to K A delta theta delta X. K is where is K? Oh, 80.4. Area, they gave us the area is 4.6. Temperature change is how much? 3 degrees? All over the thickness, which was 4 by 10 to the minus 3. Right? So that is the power of Vienna, that's the rate of heat of conduction through the stone wall. How much is that? Sorry? 277,380.
Yeah.
Right? That's in watts, right? The net rate of heat loss from the stove, assuming it's a black body, right? Right, so pay attention to the heat loss of the stove, right? What will be the value they're using? Right? So it's being radiated from the stove to the air, right? So therefore, we're going to use P is equal to Stefan constant by the area by T1 to the fourth minus T2 to the fourth. Right? You have to include the air because it's going from the hot wall to the air, the radiation. Right? What was Stefan constant again? 5 points by 10 to the minus. By area, the area is 4.6. Right. Right. We have one little problem here. The temperature must be in Kelvin. Right? Pardon me? But if we look back at the notes while we were reading, it said that the temperature is absolute temperature. Right? Temperature is supposed to be absolute temperature. Temperature is always absolute. Okay? So check it back now, please. Check it back, please. Temperature has to be in Kelvin. Right, sorry. So yeah, so T1 will be the exterior of the wall. What is 647 plus 273.1? Don't forget that 0.15, right? You know no longer 0.5, right? We're using 273.15. How much you got? Put you put T1. T1. Sorry. Very good. 923.15 to the power of 4 and then minus it at 30, right? So that would be what? 303.15 to the power of 4. 30 degrees, and now the temperature is surrounding it. 30 plus 273. 30 plus 273. You get all you want? When you focus on how long on that calculator. Plug that in. All this is part two, huh? All this is part two. So it's in the calculator. So you see why it's good to have a nice calculator, a good calculator, right? You don't know. Oh, you have some more again? Let's just put the calculator. So again, for that second part. How much? 187. 1.867 by density. And it's 5. Right. Question now. Next part. Right. Marquis, help me out here. Read part 3, right? And tell me what you think is the answer. Part 3. What do you think is the answer to part 3? Yeah, today, for class finish. So, alright, so let's start with it. So the heat from the stove loses, the heat the stove loses by combination of conduction and convection, right? What is the heat it loses by conduction?
2773.
Right. But convection, you're not seeing anything, right? But what would that radiated heat do? And that radiated heat will warm the air. So technically, what's created? Convection. So really and truly, the heat lost by conduction is 277380. And the heat that's going to cause convection is 1.87 by 10 to the 5. So therefore, the heat lost by the stove will be the sum of two of them. That's okay? So yeah, let's just sum them up. All right, copy it down. One more to try. Any questions online? The heat loss by radiation. So there's a next question I wanted us to do, but I was watching the wrong module all the time. What's the module? Alright, the next question was very similar. I just give me 1 second, tell them, let me see if I have it on the iPad. Alright, I do have the question, if I get it, we'll do it during the week, right? Alright. I do have another question. See it here. Alright, let's try this one instead.
Was on the right? Wow.
Yes, yes.
Great, Ryan.
Try this one here, please.
Now we can meet up twice more.
Yes.
Yeah.
Try that, please.
They're right.
That boy, Right, so it's not here. Right.
Oi, dahil sa dahil yung control ng function din, tapos ini Elijah. Yeah. But it's something that she like to get aside. And it was us. Yeah. But it's tough when it's like month. Like put still now she come for like 5, 6 topics. But like by lower school. That is oh okay right. How you do? Tell me something. Oh what? Tuesday try to do it.
I don't mind. I'm not going to take
Oh. So yeah. Do we have this intent? I don't have it sure. I know but if you don't good with that, because during like exam time where please do this after going to that thing online.
Right, it'll be your own here until you want to go right.
Okay. Oh, so it's illegal to work before.
How long have you traded?
Yeah.
I got just do what? I didn't like it.
Yeah, you see that?
Like last day.
Yeah. Apa dah ini pretty cool about that. It's quite they do it, right? I don't we let me make sure that you well, it's at 6 and 9. Yeah, 6 and 9. You guys come in or still? Oh, he comes to. Oh, okay.
Most of them think that people like
Yeah.
Steve, okay. Might be that's it. Steady with the country. You want out.
Yeah. So I think we're explore next week. Oh, wait, before the next week.
Next it's 2 rooms, Jordan.
Okay.
It's 2 rooms, we went around 5 and 6, we went around.
Okay.
From that. So what we can do is I will show you what it
Yeah.
Okay. Or if more the phone file.
Two, 3, 4, 5 upstairs.
All right,
Yeah.
Peter, you all done? No, you're not. Hurry up, my please. Because we have not taken the Mara, I told you my way.
Yeah. So what is it?
Hurry up. You're done? So they want you to find the surface temperature of the hot plate. So that's kind of similar to what I did before. How heat beam transferred here? Conduction or radiation? Conduction, right? Because it's in a solid.
So we are defining radiation is.
You have to find nothing being radiated.
Yeah, but and they asked me for one.
Yeah, well, if here is the final temperature, then the one here, right? So you know the final, well, yes, and the one this temperature, yeah?
And they want that temperature there, right?
Yeah.
So I don't have P, right?
You don't have P, so that's what we are waiting to find P.
That is radiation, which is P equals.
There's an next way you can find that too. Heat not being radiated, that's a liquid.
Yeah.
Okay, yeah, but what is the power that causing it to be delivered? Sorry, for it to be evaporated. So what you have to look at is what they gave you, right? They gave you how thick it is, so we know X. They gave me, we know the area, that is A. Right, they gave you the final temperature, they gave you the mass, and they gave you how long it will take. And it's water, right?
Yeah.
So anyway, for us to find the power, power is equal to energy divided by time.
You use time energy and then put it over time.
Yeah, sorry. How we get the energy? Latent theta, yeah, it's going to be ML. Right, LV, well, they would have given you LV at the beginning of the paper.
Alright.
Let me give it one time. Latent theta vaporization is, latent theta vaporization is 2.26 by 10 to the 6. 2.26 by 10 to the 6 kilograms, huh? Right? So the power being delivered, you have to use M by L over T. Why are we not using MC delta theta?
Because you have to,
Because the water is already at 100.
Yeah.
Right? The water already at 100 and there's a phase change that's happening. Right, Aaron? What the phone are we using, Aaron? You are in the class champion tension of this. Right? Champion tension, right? Right, so find the energy and divide it by the time, make sure time in seconds, right? There is no radiation there. of course, find the power first and then. Remember the question asking for the temperature of the hot plate, right? So you will need to get temperature heat. You'll need to get your temperature change first, right? So. Huh? Right, so P is equal to KE delta theta on delta X. So temperature change is equal to power by thickness all over KE. Right, so you want to get power first, which is energy on time. The energy is how much? The energy is 0.45 by LV. 2.26 by 10 to the 6. All over 3 minutes, right? 3 by 6. What you all got?
106 degrees C.
No, power. 5650.
5650, yeah.
Nice. So that'll be 5650 multiplied by thickness, which is 8.5 by 10 to the minus 3.
Right.
Power thermal conductivity,
But 50.2,
and A is your area. What's the area?
0.150.
So what you all got for temperature change?
I guess 6.3.
Anybody else get up? Yeah? 6.3? Yeah? No, tell me where you have temperature change.
6.3, yeah. 6.378.
How much?
6.378. 6.378.
6.378.
Yeah. 6.38.
6.38, right?
Yeah.
Bring it up. Right, 6.38, right? Aaron, the temperature change is 6.38. So what is the temperature here on the hot plates? 100? No, that's temperature of the water. Added, right? So you'll get 106.78. Right? Remember the hot plate should be. Remember the hot plate should be at a higher temperature.
106.
106.3. 3. Right? You all got that, Katrina, Kalina, Dylan? You all got that value there? Right, so that will be the temperature change. Right, so remember in questions with heat transfer, you have to remember when to use conduction and radiation, or when to use your heat capacity formulas and latency formulas, right? After heat transfer, we have something to do called ideal gas equation. All right. Today we'll go through the theory, and then we'll focus on questions next day on this, right? Everybody right there?
Yeah.
Bye-bye. Which one? Power is 5650
Yeah.
multiplied by the thickness, which is 8.5 by 10 to the minus 3, divided by K, which is 50.2. K is 50.2, and the area is 0.15. Final answer there is 6.38. Then it add 100 to it. And you'll get temperature of the plate. So the final answer is 106.38. All right. So the last thing we have to do for today is we have to take a look at right. We have to take a look at right. We have to take a look at ideal gas equation. Right. Everything here shouldn't be that difficult, right? Chemistry people, you all may have seen it already. But during at Form 5, we said that for a fixed mass of gas, right? Form 5, we said this, right? For a fixed mass of gas, we said that pressure was inversely related to volume. Remember that? Gas laws.
Yeah.
And we said that pressure was proportional to temperature and volume is proportional to temperature. Right? And if you combine all three, what they came up with, Jacob? General gas law. They came up with the general gas law. General gas law says that PV on T is constant. That's okay? I'll tell you. Yeah? So this law tell you, let's come here. Right? General gas law is given by PV on T equals to K. All right? But this law only holds for fixed mass of gas. What would happen now if we change the mass of the gas? Right? So if the mass of gas varies, right? So if the mass of the gas varies, then we have to consider what? If I keep adding in gas, what do I have to consider now? The amount of moles. We have to consider moles, or we have to consider number of particles. Okay, so now PV on T will no longer be equal to K. It will be equal to the number of moles by a constant called molar gas constant. R is your molar gas constant.
22.4.
Sorry?
22.4.
22.4.
24.6.
8.31. What is it? 20.
That's not the no, that's the
Right? Yeah, so it's 8.31. That would be okay, but listen, fine, like you. All right, so that's molar gas constant, or is also equal to, sorry. So more formally, you'll see the formula as PV is equal to nRT. This is known as the ideal gas equation.
and our
Yeah. That's called the ideal gas equation. So we know what P is, right? P is pressure, V is volume, T is temperature. R is the molar gas constant, and N is your number of moles. Right? Oh yeah. How you go from number of moles to number of particles?
10, 6.0 by 10. Oh, thank you.
Multiply,
Yeah.
multiply. Right? So if number of moles, if number of particles, capital N, if number of particles is equal to number of moles by Avogadro constant, then what you say? Remember what you use, no? So PV is equal to, I replace it N. N is bigger N over Avogadro constant by RT. Watch how the formula changes slightly, right? PV is equal to NR over Avogadro constant. Do me a favor now. Just divide 8.31 by Avogadro constant. Tell me what you get. Yeah. Divide 8.31 by Avogadro constant. What you got? 1.4 times 10 to the minus 23. This here is a new constant. K. K is called your Boltzmann constant. So PV is equal to NKT. Right? Go around the top somewhere. They have 1.3, right? So they're used to that.
Yeah, it's 1.3. 3 is bad. It's really 1.3 times.
Yeah.
It's the same.
Try that there.
No, okay. Okay, I'll triple another guy.
Oh yeah. Copy that down. Right, so of course, what we're going to do next is we're going to try to apply all those things, right? So the two new formula for unit 1 is PV is NRT and PV is NKT, right? When you think you'll use this one, Aaron, as opposed to this one?
They have no particles.
Huh?
They have no particles.
So when you have number of particles, you're going to use this. When you have number of moles, you're going to use that. All right. So it's important you know when to use the particular formula, right? All right, and then we'll extend onto this. We'll add some more onto this, right? If you go to the notes, right after this, there's a proof. I want you to read that proof for homework. Right? I want you to read that proof for homework and see if we can explain it. All right, so we'll stop there. Everybody have this?
Yeah.
Right, most important, these two, although we use this, we still use this relationship, okay? So once you see fixed mass of gas, you could use those, you could use the general gas law. All right? All right, next day we'll continue.